7.61, we're looking at linear programming. So let's get a little bit of an introduction. Many applications in business and economics involve a process called optimization, in which you find the minimum or maximum value of a quantity. In this section, we will study an optimization strategy called linear programming. A two-dimensional linear programming problem consists of a linear objective function and a system of linear inequalities called constraints. The objective function gives a quantity to be maximized or minimized, and this constraints determine the set of feasible solutions. For example, one such problem is to maximize the value of z equals ax plus by, which is the objective function, and it's subject to a set of constraints that determines the shaded region shown below. Every point in the shaded region satisfies each constraint, so it is not clear how you should find the point that yields a maximum value of z. Fortunately, it can be shown that when there is an optimal solution, it must occur at one of the vertices. So to find the maximum value of z, evaluate z at each of the vertices and compare the resulting z value. So that is what we are focusing on today. So each of these are the vertices, and so then we would plug it into our objective function. So this is the general rules of how to solve a linear programming problem. We have to sketch the region corresponding to the system of constraints. So we do need to sketch. The points inside or on the boundary of the region are feasible solutions. Then we have to find the vertices of the region. And 3, evaluate the objective function at each of the vertices and select the values of the variables that optimize the objective function. For a bounded region, both a minimum and a maximum value exists. And then for an unbounded region, if an optimal solution exists, then it will occur at a vertex. Let's try an example here. Solve a linear programming problem. We're going to find the maximum value of z equals 3x plus 2y. That's our objective function, but it's subject to the following constraints. So according to what we just read earlier, what we need to do is sketch the region according to the constraints. So we need to sketch all these and then shade as it states. So let's start with the x plus 2y is less than or equal to 4, because we know x is greater than 0, y is greater than 0, so that just tells us we're in quadrant 1. So a couple ways you can think about this. You can think about this as you can graph the x-intercepts, or you can convert it to slope-intercept form, whichever you are most comfortable with. Let's go ahead and convert this to slope-intercept form. So 2y is less than or equal to negative x plus 4, or divide everything by 2. So y is less than or equal to negative 1/2 x plus 2. So here is this line that's solid. It's going to be less than, so we know we're going to shade below that line. So just kind of, so I know I'm going to shade below that line. And then let's do the next one. X minus y is less than or equal to 1. So x minus y is less than or equal to 1, or negative y is less than or equal to negative x plus 1. Or dividing by negative, y is greater than or equal to positive x minus 1. So in this case, it might be nicer. I mean, you know that negative 1 is down here, and then you have a positive slope. You can think about the x and y intercepts as well. So when y is 0, we know that x is 1, so we know that is true, and then we know our slope is 1 over 1. So we know y is greater than this line in this case. I'm going to do it that way here. So greater than, that means we're going to shade above that line, and we're going to shade in here. So our solution region is going to be this space here. So that's the first thing. We sketched our graph, and then we need to label the vertices. So here we can find the vertices very quickly. We can read it. So this is x is 0, y is 2. And then here, this is x is 2, y is 1. Then we also have 0, 0 here. And then we also have this point, which is 1, 0. And of course, we had the constraints, y is 0, and x is 0 that I could draw here. So after we draw it, the next thing we're going to do is we're going to substitute each of the vertices into the objective function. So let's plug it in. And then we're going to find the maximum value. So we're going to find which one is the largest value. So 3 times 0 plus 2 times 2. I'll just plug it all in. Z is 3 times 2 plus 2 times 1 is equals 3 times 1 plus 2 times 0 and then z equals 3 times 0 plus 3 times 0, and there's 4 points there. So maximum value. So we have 4, this is 6 plus 2 is 8, and then 3, and then 0. So therefore, we have our maximum value here at 8. Max at 8 when x equals 2 and y equals 1. Now, it's not something that you can just see it and go, oh, automatically this is the maximum value. It's not true. You actually have to plug it in order to find what is the maximum or minimum value. So try this example here. Find the maximum value of z equals 4x plus 5y subject to the following constraints. And so go ahead and graph this first and then plug it in. So you should have found that the max is at 30. Max is 30 when x is 0 and y is 6. And this one was nice to graph using the intercepts, just to kind of talk about that. So I know if I make x 0, y is 6. If I make y 0, x is 6. And so that was the fastest way to graph that instead of converting it. Then I know it was less than, so I know it's shaded in here. And then we also have to graph x. It has to be greater than 0, y has to be greater than 0, so we know that it's contained in this region here. And then I labeled my vertices 0, 0, 0, 6, and 6, 0, plugged each in, and then I found this here. So just a little bit more information. In example 1, consider some of the interior points in the region. So here, looking at the interior points in the region, you'll see that the corresponding values of z are less than 8. And so if you plugged in some of these values like 1, 1, you notice that it's 5. If you plug in a half and 3 halves, you'd get 9 halves and so forth. So notice that, this is why that the maximum values must occur at a vertex. So if we write the objective function, this function, in slope-intercept form, notice that the y-intercept is z over 2, and it varies according to the value of z. So this equation represents a family of values, each of slope negative 3 halves, right? The slope here of negative 3 halves. Of these infinitely many lines, you want the one that has the largest z value while still intersecting the region, determined by the constraints. So in other words, of all the lines whose slope is negative 3 halves, you want the one that has the largest y-intercept and intersects the region as shown in figure 7.25. And so notice that from the graph that this line will pass through one point of the region, and in this case, it's this vertex here. So it always has to be at a vertex.